record this because we're going to be talking about some concepts that might be a bit less familiar to y'all. So what we are going over the next chunk of this class, we are going to be talking about sort of advanced modeling of fluid is the name I gave to this portion of advanced modeling of fluids is the name I gave to this portion of the class when I was planning it out. And what that means is we're going to be talking about various ways of modeling fluids and talking about fluids that are perhaps a little bit more theoretical than what we've done before and sometimes require a little bit more advanced math. Most fluids textbooks put this stuff at the beginning because they think, oh, this is fundamental stuff. We zoom in and we can model how the fluid is working on a microscopic fundamental level, right? You'll notice that, for example, the stuff we're going to talk about today is chapter 4 of your book. I chose to put it at the end for a few reasons. And one of them is that I wanted to sort of front load kind of big picture stuff. And also front load things that you are more likely to actually do as if you go out after you graduate from here and go and get a chemical engineering job. But we're going to talk about this and we're going to learn some sort of fundamental things about fluids, and you're going to, if you like a lot of the stuff, and that's not to say we're not going to do any practical problems with practical applications, we are. But if you like some of the stuff we're going to do and want to do more of it, you should consider taking the graduate transport class, maybe in your senior year, right? Because if you like this stuff, you'll like that. Okay. So one thing I want to just talk about before we get into this is my experience. I always do derivations. We always derive all the equations we use in my classes. And in my experience, some students kind of get a little bit bored by that. They want us to skip to the actual problems we're going to do. Why do we do derivations? Does someone have a thought about why your professors love to do derivations in class?
I think sometimes it's easier to remember the equations if you know how to derive them.
Well, yes, that's 100% true. In fact, sometimes I forget what the actual equation was and I just rederive it. You actually don't have to remember as much as if you remember the fundamental things. Essentially, if you remember F is equal to MA and a few other things, then you can derive a bunch of other stuff. You don't have to memorize as much. That's part of it. And also you just kind of understand where the equations come from. And also you can understand when the equation in the form you have it written down in your notes doesn't apply. For example, if it was derived assuming incompressible flow, for example, and you have a situation in which flow would be compressible, you know that you can't just simply use that equation you've written down. Okay, or remember back when we did force on a vertical wall, okay? We did the whole equation with the integration, and for a rectangular wall, which is what a lot of walls are, it ends up being 1/2 rho GHA. But since we derived it, we know that if you change the shape and it's not a rectangle anymore, then you can't use that. Whereas if I just gave that equation to you and said, this is the force on a vertical rectangular wall, that might not sink in as much. Why do we study the theory behind all this? Okay, why don't we just do example problems all day? Why do I want you to understand the theory behind all of this? KK, I like your screen name, by the way.
So we can understand new problems.
Yes, Hunter, so you can understand new problems, which is also why I mentioned grad school. But the reason you get into a lot of theory in grad school especially is grad school is where you go to tackle new problems, like brand new, exciting, big problems. And that could also happen in your career and other places. Also, one thing, if y'all remember anything from this class, I hope it is the concepts, because if you know sort of the concepts, it's easier to reteach yourself everything else later. And also, there's something valuable, I think, in just learning to see the world around you in a technical way. So I think there's something valuable in being able to look around and see forces and energy interacting around you, and it kind of changes the way you see the world. And I think that there's just value to that in and of itself, even if you just end up retiring at 30 and playing video games for the rest of your life. Your mind has been expanded. Okay. There are many ways of describing fluids. Today, we're going to talk about some ways of describing fluid kinematics. So fluid kinematics is the motion of fluids. That's all. We're just talking about motion now. Forces and energy aren't coming into this. And kina means motion, just like kinetic energy or kinesthetics or things like that. Kinetics, kinematics. There are various ways of mathematically describing fluid motion. And as with all kinds of descriptions, these depend on your frame of reference. And we're going to talk about a couple different frames of reference we can use to describe the motion of fluids. Okay. There's two basic ways of looking at this that are commonly used. One is called the Eulerian description of fluids, after Euler, it's a mathematician. So we define some control volume. So we define a volume in space, and fluid comes into it and out of it. All this time when we looked at a pipe and we said, what's happening in this pipe? We were treating it as a volume, a control volume, because water flows into the pipe and out of the pipe, and we're not following the water along. We're looking at that volume in space as fluid comes in and out of it, okay? And then we define field variables that describe how different properties change over that space, over that volume. The other way is called the Lagrangian way. So here we divide the fluid into parcels of fluid, like little chunks of fluid, and you call that a little chunk of fluid, you call a fluid particle, and you track the movement of those different fluid particles. So they each have some velocity vector and some position vector, and they move around. So now you're following the fluid itself rather than just looking at the volume. Now write those down, Eulerian, Lagrangian, because those are just guys' names. And you're gonna need to just learn how to keep straight which goes with which. And in about 5 to 10 minutes, I'm gonna ask a couple random people to answer some questions about whether an example is Eulerian or Lagrangian. So write it down. And let's actually look at this what do those words I just wrote down mean? So here we have the Eulerian description. And remember I said Eulerian, we just look at the volume and fluid goes in and out, and you have field variables. These are two examples of field variables, and we have a chart showing, so this would be in a 2D space. We got rid of their dimension. And you can see a pressure field and a velocity field. So what that means is you go to some XY value, and you can see what the pressure is there. Same here. As I said, the field variable shows what this property is across this control volume here. You could describe it with some equation that has X and Y in it. It could also have time in it. Okay, this could also change with time. Also, one thing I want you to notice, pressure is a scalar property and velocity is a vector property. So from your math class, what's the difference between a scalar and a vector?
Vector has direction.
Vector has direction, a scalar does not. Okay, so pressure, there's just some number everywhere. But with velocity, which is a vector, there's a number and a direction everywhere in the thing. That's Eulerian. And as I said, Lagrangian is where instead of looking at that whole volume and having some function describing what happens over it, we treat the fluid as being made up of a bunch of little pieces of fluid. Now, these are not real because in reality, if you have a little piece of fluid, it's made up of millions and millions of molecules that don't necessarily stay together. So if we define some little chunk of fluid as a fluid particle, in real life, it's gonna deform and change. And if we're trying to be super realistic, that can be hard to keep track of. But you can still get some pretty useful modeling out of this model. Okay, everyone sees this video. Go. All right, so you can see that if we just treat the fluid as being made up of a bunch of little particles, it still flows like a fluid, right? So it's still modeling the flow of the fluid, even if that's not exactly realistically how it is.
Is this how like Pixar animates their water?
Probably. Well, Pixar probably animates their water using the Navier-Stokes equation, just like video game well, I know, video game companies, their water has to change. In a video game, the water has to change based on what you, the character, does. So they have to have some kind of equation that shows how it will change in response to what you're doing in real time. And so they use a simplified version of Navier-Stokes. Pixar, I bet, does too, but maybe they would use something else. Not sure.
Okay.
I'm going to look into that, actually. That's kind of an interesting question.
I don't know about water, but in the math building, they have on those TV things, they have a little snippet that they play about how a math grad from BYU calculated or made some calculations to do wind in the movie Frozen. And that contributed to them getting their Academy Award for Best Animation. Okay,
wind and water, both fluids, they both work according to the same methods, right? It's actually interesting. I have some reading I'm gonna make you do later about the video games I was mentioning because there they have to do the calculations really fast. And so they have to do some mathematical, come on, open. They have to do some mathematical approximations in order to be able to do it in real time. Okay, and this second video, it just shows a similar, actually, so this does show you how NVIDIA is the one doing this, right? So this could be used in a video game or an animation. And we have, okay. That is air around a car. Again, actually, I bet you couldn't do this in real time. I bet this took like a few weeks on a NVIDIA GPU in order to do this, but still, that's cool. All right. Okay, so those are both Lagrangian descriptions of the fluid. One thing we might be interested in is the rate of change of some property, and you can look at this in a Eulerian or Lagrangian way. So think about a leaf on the river, right? How does and let's take the velocity as an example. That's an easy one to think about. How does the velocity of the river change?
Like the whole river?
The whole river, or at least this piece of the river we're looking at. We define some square of the river, and we say that's our control volume. So how does the velocity of the river in this square we're looking at change? It's faster in the middle, says Christian. Okay, so it's an ocean of different dots, funny. Faster in the middle, says Christian. Yes, so that means that it changes with the position, like X and Y. So for example, if this were the banks of the river and this was, we call this the Y direction, then as Y changes, the velocity changes because it's faster in the middle. It can also change with time. So for example, there could be a big whoosh of melted water running down from the mountains that whooshes through everything and just makes the velocity everywhere higher for a second. Okay, so it can change over space and over time. Is that Eulerian or Lagrangian? I am going to call on a random person, Johnny Pershing. Hi.
Howdy.
Hi, howdy. So we're talking about the velocity of the river changes. Is that a Eulerian or a Lagrangian way of looking at it?
Well, what's throwing me off is that our picture is definitely like a confined area. And I feel like velocity could be a field variable. So I think that's what I'm going to go for. I'm going to go Eulerian on this one.
All right, good thinking. Velocity can and is a field variable, right? And I said, look at the square of the river. So we're not looking at some little piece of water. We're looking at the square, the whole area of the river and how the velocity changes with space and time. That's a Eulerian way of looking at it. Okay, but what about the velocity of the leaf? So this leaf is just moving around the river, right? So how does the velocity of the leaf change?
What was that? Is that still me, Professor?
Yeah, sure. Yes, Johnny. How about still you?
Okay. Well, I mean, it's obviously going to be the other one, so it's Lagrangian, but it's because we're just looking at one like pseudo particle that we've defined and seeing how that one thing is moving. So
yes, exactly. So you knew it was the other one because of the way this works, but also you are right. It's because we are following something as it moves around. We are following one. In this case, it's a leaf. It could be something physical too, like you could drop a little probe in, but it could also just be a little piece of fluid that's moving around. So as it flows through this river, that leaf is going to change velocity. If it moves into the middle of the river, it's going to start going faster, for example, right? And we can just change it around. Now, let's talk about the math of that. In Eulerian, you have F. F can be anything. It can be pressure, velocity, viscosity, I guess, shear rate, whatever. And F is a function of X, Y, Z in time. The F field can change with time, so the whole X, Y, Z can change over time. All right, and call that dF dt. So so in the case of the river, the big surge of water comes, and then the whole field will get faster, basically, right? So that can change with time. And then in the Lagrangian point of view, so we're following the leaf or fluid particle. Okay, we're saying how will F change from the point of view of the leaf? Okay, it changes as it moves through the field. That's just what we're talking about. And also the field can be changing with time at the same time. So the leaf is moving through the field, which makes the velocity of the leaf change, and maybe the field is also changing. We want to relate these 2 points of view so that if you know the function F for the field, then you can figure out how the property is changing for the leaf or the particle. And the way we do that is through the material derivative. So notice the capital D's. The capital D's are just the notation that shows that we're talking about the material derivative, which is this specific operator right here. All right, Rankin says, gradient symbol giving me math 302 PSD, oh no. Well, ever heard of exposure therapy? Okay, math 302 is coming back. And another reason I moved this stuff towards the end of the semester is some of you may be in math 302 right now, okay? So this relates to Lagrangian and the Eulerian points of view, like I was talking about. It can be applied to any property, and it represents the rate of change of that property as we follow a fluid particle. So talk a little bit more about how that means in a second. Okay, a little bit about math. As Rankin was saying, that's the gradient symbol, that's the del operator. So gradient F or del F indicates this, all right? And I use I hat, J hat, and K hat to represent the X, Y, Z vectors. And that's just what I'm going to be using over the class. There's other notations. This is what I'm going to use. It's what the book uses as well. Okay, there's also a velocity vector in there. And I am going to use U, V, and W for the X, Y, and Z vectors. You may have noticed in this class that sometimes I use V for velocity and sometimes I use U. And maybe part of you thought, why U? Where did U come from? This is where U came from. Okay. So another way you might see it is Vx, Vy, Vz, but they mean the same thing. In fact, I'll write that down. So UVW, it's also the notation your book uses, and I kind of like it because you don't have to put a subscript every single time. Also notice that V has this bar over it to show that it's a vector. We're using vector notation. All right, so what's V dot del F? Speaking of math 302, we're doing a dot product of two vectors. What do we get? In fact, actually, you know what, Rankin? Since you made that comment about math 302, what do we get when we dot together two vectors?
Yeah, so we have, so it would be like the derivative of f in terms of x times the x component of the velocity plus y and y plus z and z.
Yep. Yeah, exactly. U times df dx plus v times df dy plus w times df dz. Now here's a little bit, one more level to the question. Will this be a vector or a scalar, this answer when you got it?
Scalar.
Yep. Okay, Connor, you know that when you dot together two vectors, you get a scalar. That is why you said that. But it's actually, in this case, it depends on what df dx is, df dy, df dz. Because sometimes df dx is a scalar and sometimes it's a vector. And if it's a vector, this will turn out to be a vector. We're going to see an example where that happens. But that's why I wanted to bring it up, is because you remember that dotting together two vectors makes a scalar. In this case, it depends on what df, d, whatever actually is. Nicholas says, are we treating I, K, J as unit vectors? Yes. Now, this equation sort of looks like an equation, but I want to talk about it because it should actually make sense to us. So we're trying to figure out how the rate of change of the leaf at any point in this flow. And first of all, we want to know what F, the function of the property over the whole volume, it could be changing with time. So that's what the df dt is about. And then at this point, say the leaf is moving in some direction, let's say up there, and that is captured by the velocity of the fluid at that point. So the leaf is going to be moving at the velocity of the fluid of that point. So that shows us what direction the leaf is moving at. And then del F, that shows us how F is changing in all the directions. Okay, so we have, this shows how what direction the leaf is going in. This shows us how F changes with the direction. So you dot them together and you get how F is changing for the leaf as it's going in a direction. Let's do an example. And I gave us a chunk of time to do this example, even cutting out some other concepts so we could spend a lot of time on it. So let's do that. We've got a steady, incompressible, two-dimensional velocity field, which I've given you here, where x and y are in meters and velocity is in meter per second. And I want you to calculate the material acceleration, the acceleration of a parcel of fluid at a certain point. Now, the first thing I'm going to ask you to think about is, I said material acceleration. Okay. What is F? If we're talking about acceleration, what is F?
Velocity.
Velocity, right? Because acceleration is dv dt. So F is v. And so the material derivative will be dv dt. Kind of gave that away because I accidentally had that hovering on the page, but Ian says, how would you add df/dt with a scalar if df/dt is a vector? So it won't be. Like, they'll either, because del f will only be a vector if f is a vector, or df dx or df dy or whatever, those will only be vectors if df dt is a vector. Okay. All right, so that's the material acceleration. Gonna pause here, gonna let y'all go ahead. Did you all have time to write down the velocity field? Because you need that.
Could you go back to that real quick?
I'll go back then. Okay. Give me a little bit of time, go forward a little bit. Now, the question said that the flow is steady. So what does that mean? What point did we need to calculate at? It was x equals 2, y equals 3. Okay, flow is steady. What does that mean we can do? Let's actually ask a random person. Andrew Hall. Hey, Andrew.
Hello.
Okay, so what do I mean when I say the flow is steady? That was part of the problem statement.
The velocity vector isn't changing?
The velocity vector isn't changing in what way? Because it changes in X and Y directions.
Right, but at each of those points, it's not changing, it's consistent.
Yes, at each of those points, it's not changing with time. So that means that at every point, the velocity isn't changing with time. What does that do mathematically to the material derivative equation I wrote out?
That means we can eliminate the dv dt.
Yes. Yeah. Right. Okay. All right. Keep going forward. Someone tell me when you have an answer for maybe not the final answer of what it is at that point. And then after the first person says they've done it, I'll wait a couple more minutes. And okay, Rankin says he's got a 2.4. So here's the thing, Rankin, you got 2.4. That's not the entire answer. Meters per second squared. So yeah, the units are important. I'm still fishing for something else.
You need the direction too, right?
Yeah, you need direction too. All right, and Zachary gets 1.68i, 0.72j. Okay, so that's a more complete answer because it also has a direction. Acceleration has a direction too, which a lot of times in this class, we just use the magnitude of everything because direction doesn't matter as much to us, but now we're zooming in to the microscopic level, and we always need to know the exact direction of everything. Okay. All right. So I separated out U and Y and V. Then W, the Z one is 0, by the way, because this is two-dimensional flow, which could just mean that in the Z direction, the velocity doesn't change with that direction. Find dV dx. And this was what I was talking about, how the derivative of df dx could be a vector. Dv dy, like so. And then I multiply u times dv dx and v. I'll put little thingies so you can tell it's a v instead of a u. dv dy, like that. Okay, Nicholas says, what's the difference between j and j hat? No, the hat is just notation that's often used to mean it's a unit vector. It's just notation. Sometimes people bold them. So like instead of having a little hat on it, it's bold j, bold I. Sometimes it puts a little bar over them. It's just notation. Okay, so you multiply this across, you should get 0.4 plus 1.6 r, let's see. Yep, 0.4 plus 0.64x. Actually, give me a second. 0.8 times 0.8. Okay, all right. Okay, 0.4 plus 0.64 xi plus negative 1.2 plus 64 yj.
Dr. Nick,
Yes, Nicholas.
are you writing something right now?
Oh, can you not see it? Give me a second. Can you not see? Do I need to reshare the screen?
Yes.
Okay. Okay, like so. So at x equals 2, y equals 3, we plug those in. 1.68i plus 0.72j, unless I made some sort of algebra mistake, that should be right. So let me know if I did, but everything added up right. This is one way of expressing the answer. There is a different way as well. What would be the other way of expressing the same answer?
Do we put like ax is equal to 1.68 and ay is equal to 0.
Oh yeah, you could do that. That would also work. You could write ax is equal to 1.68 meters per second squared, and ay is equal to 0.72 meters per second squared. Same way, same answer expressed a different way. And another way is you can take the magnitude, you can show the magnitude and the direction of the acceleration. So how would I find the magnitude of this acceleration? It's got an x component and a y component. Oh, what were you saying, Ethan? Sorry.
So you just square them both, add them, and take the square root.
Yep, because the magnitude is also the length of this sort of hypotenuse I could make between them. So that shows the actual direction of the acceleration. By the way, this also, just on a basic level, this shows us that if one's going positive to the, x is positive to the right, y is positive up, then put them together and the direct overall direction is sort of up and to the right. On magnitude, I believe it's 1.83. And then you also, but you have to, if you don't include the direction, that you haven't completely answered it. So you can find this angle there. How do you find that angle?
Tangent.
That would just be the inverse tangent of the y over the x, right?
Yep, inverse tangent of y over x is the easiest way. Or inverse sine, inverse cosine if you do that right, but arctan of y over x, 23.2 degrees. You know what, we are finishing this earlier than I thought. We could have also talked about streamlines. It's cool though.
Dr. Nickerson, could you explain why when you take the dot product of the velocity vector and the gradient of the velocity vector, you still get a vector out?
Yes, so the reason why is because the reason why is because you took the dot product and you got this. And we all agreed that's what you get when you do the dot product. That should, in fact, I'll go back again, all the way. Okay. We all agreed that this is what you get when you took the dot product of the velocity vector and the gradient of the velocity of f. Okay, that makes sense to us. And so then it has df dy, df dx, and df dz in it. And df dx can be either a scalar or a vector. So if f is a vector, df dx will be a vector. If f is a scalar, df dx will be a scalar. So in this case, as I said, we all agreed on that. The derivative of dv dx is a vector. And so therefore, when you plug that in to that dot product we got below, you get a vector out. Now, let's say it was something else. Let's say it was temperature, for example. Temperature is a scalar value. So let's say instead of this, so let's say we had like T is equal to 3x plus y. Okay, then what would dt dx be? Three. And dt dy would be 1. Okay, and so those are scalars. And so when you plug them in here, if you plug them in right here, it would just be 3 times 0.5 plus 0.8x, and there wouldn't be any direction to it. So that is why you can end up with a vector.
Okay, thank you.
All right.
Can I ask a question?
Yes, you can always ask questions all the time.
That's good, thank you. So I'm still confused, like what this means. It's like these calculations make sense, but like, what does it mean that we found the material acceleration?
Okay, so I'm going to give you a practical example here. So acceleration, we might care about what the acceleration on a little piece of fluid is for lots of reasons. So for example, that gives us the force on that piece of fluid on that space, right? Because force is mass times acceleration. Okay, and so this then would give you the acceleration of the piece of the piece of the velocity right there. And let's say it was a leaf. Remember the leaf? Okay, the leaf has some mass. So if you found the material acceleration of the leaf multiplied by mass, you get the force on that leaf. And so you could figure out what the force on the leaf was wherever it was. Like if you know the X and the Y position of the leaf, you could figure out what the force on the leaf is using this. Or
also, could you, if you knew the initial position and initial velocity of the leaf, could you predict its path if you knew the material acceleration?
Okay, so, yeah, that could help. We are going to talk briefly next week about predicting the path of things, because that's something you can do. And that's an interesting thing. Or let's say, this is an example I saw recently, and I thought of making a homework problem, but I didn't. So let's talk about it right now. Okay. Let's say we have a weather balloon, right? Here's the balloon. It's got a sensor on it. And there's some 3D velocity field, like E is equal to U. Okay, there's some 3D velocity field that's the velocity of the air that's moving this balloon around, and it's just moving around in that field. And we want to know the rate of change of the temperature of that balloon, which would be just that normally we write it as dt of the sensor that's attached to the balloon. We want to know that because maybe that goes into our model that predicts what the weather's going to be, right? Something like that. So what we would do is we take the material derivative, and so an equation we've used for temperature and atmosphere before is T is equal to T naught minus G Z, like that. Okay, because the temperature drops as you go higher. So this would be the temperature distribution of the air, okay? And we'll say it's steady state, so that goes 0.
Then what is that last term in the material derivation equation again?
Okay, so this would be the gradient of air temperature. So T here represents the temperature distribution through the air, right?
So it's just the fact that as you go higher, it's colder?
Just in this case, yes, because in this case, T only depends on Z. It doesn't depend on X and Y in this case we're looking at. So that's what that shows. It shows that as you get higher, you get colder. Maybe there could be like, maybe there's like a lake and over the lake, it's colder than not over the lake. And so then there would be an X and Y in that equation too. Okay, but that's what it shows. In this case, it shows as you get higher temperature, it gets colder. Okay, and so that would turn into V U times dt dx plus V dt dy plus W dt dz. And what's dt dx? It's 0 because temperature doesn't depend on X. So in this case, it only ends up depending on the Z velocity is the only thing that changes the rate of, that affects the rate of change of temperature on this balloon. Like that. But yes, so again, this is any time we would want to find the rate of change of something on a piece of fluid. So maybe we want to know the force on that piece of fluid so we can do a force balance, or maybe there's some kind of sensor that's moving around and we want to know the rate of change of something on it.
So something else that confuses me is how like the dt dt is 0, but
okay.
Yet we're getting not 0. Like I guess I'm confused at the
Yeah.
difference between.
So that's one of the reasons we defined this in the first place, because I wrote little dt dt of the sensor. Okay. Whereas this one is the ddt dt of the air, of the whole air. And that's one of the reasons we did this, and we did the different notation with the capital D in the first place, which, speaking of which, I forgot to make that a capital. Okay. Right. So the temperature of the air is not changing at any point. And that's the whole thing. So actually your question shows why we defined this in the first place. The temperature of the air is not changing. The temperature of the balloon is changing with time, because the balloon, as time goes on, the balloon is moving around.
And so big D always represents the property of the particle, while small d represents the property of the entire field.
Yes, that is the notation we use. And that is the reason why we use that big D, is to keep those straight. In this case, the little d, property of the entire field, big D, material derivative, property of the particle.
So that arrow that you have pointing to the big, so on the left side of the equation, where you have an arrow pointing to it but no label, what would the label on that be?
Oh, just material derivative. Or I could also say, yeah, it's the rate of change of the sensor. Mm-hmm. And that's the whole point. As I said, this is why it relates the Lagrangian point of view of the Eulerian point of view. It's because those things are different, and this puts them together. Now in your homework, you're gonna do a problem that I wanted you to do one that's a little bit more mathematically complicated. So it's gonna have time in it and it's gonna have 3 dimensions. But, so it will be a little bit more mathematically complicated, but you should still be able to do it because you took 302. And the steps are gonna be exactly the same, where you figure out what U, V, and W are, and then you figure out what dV, dx, dV, dy are, and dV, dt. Then you put them together, get the material. So a little bit more math. I will upload this recording. I made sure to record this because I knew we were going to talk about some stuff that you guys were going to think was super weird. It's not though, you have done this math before. It's just, there's lots of notation and things as you see all the numbers and all the vectors and things and you go, ah, but you've done it all before.
Dr. Nickerson, with the material derivative, is it only ever with respect to time, or would you be interested in like dt, dx, or something like that?
You know what? That's a good question. That's a really good question. Maybe you would be. I don't see a reason why that wouldn't work.
Okay.
It might be set up in a slightly different way, but certainly something similar could happen.
Like maybe instead of adding df, dt on the right-hand side, you'd add like whatever you, df, dx, or whatever you wanted. I don't know.
Yeah, something like that. And maybe I think df, dx would probably be just u, like if you were trying to find df, dx like that. I think that's not the capital. What was I talking about? See, yeah, if you're trying to find that, I think it would just be like u. So the x component of the velocity times df, dx like that. I think it would just be that part. But maybe there could be something else, like maybe it depends on temperature, for example, right? And so it would be something like df, d temperature is equal to df, d temperature plus something like that. I'm not sure exactly how it's set up, but there might be something similar.
Okay.
Mm-hmm.
Dr. Nixon, something that doesn't quite make sense to me about the material derivative is so like the time dependency, the df/dt is just, you know, there by itself, but then everything that relates to position, we dot that with the vector. What is dotting the gradient with the vector do for you? Like why do we have to do that step?
Because
instead of just adding the rates of change at, you know, df dx, df dy to df dt?
Because the particle is moving, that's what it does for you. The particle is moving at some velocity v. And so that velocity there, that tells you what direction our particle is moving. So for like, okay, let's say that, let's use temperature again. Let's say temperature is 200 right here, and that it's 300 right here. So if I am moving in this direction, my temperature is going from 200 to 300. Whereas if I'm moving in this direction, my temperature is going from 300 to 200. And I guess if I kept on going this way, it's going to whatever that is. So that's what dotting it does. The velocity says what direction I'm moving in, and the gradient f tells me how it changes in the direction I'm going. So like, okay, 200, 100, 300. If I'm moving this way, my temperature is going up. I'm moving this way, my temperature is going down. That's what the velocity part does.
Right, okay.
Mm-hmm.
That is making sense. But it's not like your initial velocity.
No, it's not the initial velocity.
Right? It just kind of defines where, like, at what point you are in the field.
Yes, because the velocity field, that tells you what the velocity is at that point. So my velocity field told me that right when I'm right here, my velocity is +2. So I'm going this way. So it's not initial velocity. It says when you're at x equals whatever, y equals whatever, this is what your velocity is. So it's a way of, like, we could have some variable that we call v naught of the fluid particle. And then we would use v of the particle is equal to v naught plus vt plus 1/2 at squared. And then v is changing and all this stuff. We could do that. But if we know that v is equal to 3x plus 2y as you move around, we don't have to keep track of that. Instead, we just say if the particle is right here, then its velocity is whatever. So that's what we mean by saying that this relates the Lagrangian and Eulerian points of view, is it takes that Eulerian way of looking at the velocity, which is that at x equals 2, y equals 3, the velocity is 5 or whatever, and applies that to our particle.
Can I say something, Dr. Nickerson?
Yes.
Is this kind of like maybe when you dot the v and the del f, is it kind of like a chain rule thing where, like, so if you think about v, it's dx dt plus dx dt I plus dy dt j plus dz dt in the k, and then once you times those out, the dx's cancel and the dy's cancel, and you're left with stuff that's df dt I. I think that would work, and then you're adding df dt and then plus df dt, right?
That sounds right, because remember that, like, okay, so let's say it was u d, I'm gonna use temperature again, dt dx, right? So that's the x part of this. And let's say that, and u is dx dt. Oh yeah, you just get some constant, yeah. Oh no, these are different, because this is dt dx of the field, and this is v of the particle. So I'm not sure formally that works out how I wrote it out, but I think your idea is right, is that's basically what's happening, is that.
Okay.
Yeah.
So then you're kind of able to add each component of the v dot del f to each component of the df dt, and they work out.
Yeah. As I said, takes.
Dr. Nickerson?
Yes?
So the idea we discussed today is basically the particle being a part of the fluid. But if you go back to, like, the leaf in a river example, would you not need to translate the velocity of, like, the velocity field of the river to a force field?
So
like acting on an independent body in that field?
All right. So when I talked about the leaf, I made kind of a hidden assumption, which is I said that the velocity of the leaf is the same as the velocity of the water wherever it is.
Okay.
And what you are talking about is the leaf actually has some mass, and so the water will push on it with some force, and it could accelerate, and so it could take some time. So like if you took something heavy and you dunked it in the water, it might take it a while. It won't immediately speed up to the velocity of the water. It will sort of lag behind and stuff like that. The leaf is so light that I made the assumption that the velocity of the leaf is just the same as the velocity of water everywhere, which is the assumption that it almost instantly accelerates up to whatever the velocity of the water is.
Sure. I guess my other thought was with the weather balloon. I mean, you're going to have velocities not matching, right? Because of the mass of the balloon itself. So you'd have to turn that velocity like into the external flow concept and get a friction drag force, and that would cause your acceleration of the object in the fluid flow. Okay.
All right. Probably. So the actual answer is that you can make the simplifying assumption, and that simplifying assumption might be better or worse. And so, for example, you know, half the graduate students who come through here, what their project was this model we were using to describe the distribution of ash in a coal burner. It assumed that the ash particles immediately accelerated up to the velocity of the air or something like that. But actually there's a little bit of drag force, and so I added that into the model. And they would do it and they would say, and it made this much difference. And maybe their conclusion is, I did it and it made this much difference, and in most cases that doesn't really matter.
Fair enough.
Or it could be, and it made a significant difference, and so we say that you should definitely use this better model I made from now on.
Okay.
All right, thank you all. It's very exciting. We're going to get to Navier-Stokes soon. It's going to be great. Okay, glad. I am going to share this recording, and fare thee well.